Society for Mathematics and Computation in Music. And its location follows our alternation tradition, you know, between Europe and America. It's, you know, if you remember, Conference 2007 was in Berlin, 2009 was in New Haven, 2011 was in Paris, and then 2013 was in Montreal, and 2015, the last one, was in London. And perhaps we may add an Asian alternative in the future. I don't know, there's no plans yet, but that would be a nice extension. Now, I have to say that Mexico, and in particular my wonderful friend and mathematician and classical pianist Emilio Puebla here, has played a major role in the propagation of mathematical music theory since the end of the 20th century. My first contact and visit to the UNAM here goes back to, I think, 1999, 97, thank you. You see, Mariana, it was earlier than we thought. When I supervised, I think, Mariana Montiel's master thesis, is that correct? So I was invited here, and I was at the same hotel, by the way. And Emilio then organized the first international seminar on mathematical music theory here, exactly here in this room, after the Congreso Nacional de la Sociedad Matemática Mexicana in 2000, followed by the second international seminar on mathematical music theory in 2001 in Sauen, Germany, organized by Thomas Noll, and the third international seminar on mathematical music theory in Zurich in 2002, organized by myself, and then the fourth international seminar on mathematical music theory in Huatulco, again organized by Emilio Puebla and his collaborators, of course. And finally, in 2014, the Mexican scholars organized the International Congress on Music and Mathematics in Puerto Vallarta, which was also a successful event, and I think there is a book coming out with the contributions there. For these reasons, I think the sixth conference here of the Society of Mathematics and Computation in Music is the point of convergence of a long Mexican tradition in the art and science of mathematical music theory. We have to recognize that. Unfortunately, our Vice President, Moreno Andreatta, cannot join us this time, but the reason is not only a negative one, it's also a positive sign in the sense that he joins a major and simultaneous conference on musical analysis in Europe. So that means that our perspectives are also present in a wider context, and I think this is also a positive sign, yes? Okay, I want to express now to all organizers and participants of this conference my deep gratitude for your work and wish you a wonderful and inspiring week at the UNAM. And I have to mention now, that's very important, the organizing committee. The committee is Emilio, as I already suggested, of course, Octavio Alberto Agostino Aquino here, Mariana Montiel sitting down there, and Gabriel Parellon, I don't know whether he's here, I did not see him yet, and Roberto Morales Manzanares, Emil Awad, and Juan Sebastian Lach. And I think we should applaud them for their organizational work, and I'm very happy to pass my word to Emilio.
First of all, most welcome to Mexico City. I hope you enjoy your stay. For those who come for the first time or inquire about a conference on mathematics and music, some students, lots will come, let me tell you that our field is both a recent area of study and a very old one. At the beginning, there was a connection of numbers and musics since Pythagoras, which turned out into an effort to say things about music with certain foundation. Descartes, Galileo, Kepler, Leibniz, Euler, D'Alembert, Helmholtz are some others that appear in this scene. In the last century, acoustics and its technology were very successfully applying mathematics to music. Also computer science and some other fields like linguistics. Later, the work of Clough in 1979, Lewin in 1982, and Mazzola in 1985 inspired both music-interested mathematicians and mathematical-interested musicians to continue working in mathematics and music. Currently, it is noticeable that there are a big trend in the last 3 decades in mathematics to do not only applications, but to do new mathematics in a variety of fields of knowledge, and the field of music has been no exception. So mathematical music theory is both a recent area of study and also a very old one. From Pythagoras till the 80s of last century, very few and not very sophisticated mathematics were in the scene of music. It was when the heavy mathematical machinery was available and that the smart enough talented mathematicians used it that the recent mathematical music theory was created. One of the main goals of mathematical music theory, and I will quote some of Guerino Mazzola's thought, was to develop a scientific framework for musicology. This framework had as foundation established scientific fields. It included a formal language for musical and musicological objects and relations. Music is fundamentally rooted within physical, psychological, and semiotic realities, but the formal description of musical instances corresponds to mathematical formalism. Mathematical music theory is based on category theory, algebraic topology, in particular topos theory, module theory, group theory, homotopy theory, homology theory, graph theory, algebraic geometry, just to name some areas. That is on heavy mathematical machinery. Its purpose, among others, is to describe the musical structures. The philosophy behind it is understanding the aspects of music that are susceptible to the reason in the same way as physics does for natural phenomena. This theory is based in an appropriate language to manage the relevant concepts of the musical structures in a group of postulates or theorems with regard to the musical structure subject to the defined conditions and in the functionality for composition and the analysis with or without computer. It was until the near last 4 decades that there is consistent work in mathematical music theory. This 6th International Conference of Mathematics and Computation in Music is held here at UNAM in Mexico City. The MCM is the flagship conference of the Society for Mathematics and Computation in Music. It continues the tradition of biennial international conferences for the Society for Mathematics and Computation in Music held on alternating sides of the Atlantic. In this occasion, it is hosted by the faculties of sciences here at UNAM. The conference brings together researchers from around the world who combine mathematics or computation with music theory, music analysis, composition, and performance. MCM provides a dedicated platform for the communication and exchange of ideas amongst researchers in mathematics, computer science, music theory, composition and performance, musicology, and related disciplines. There will be introductory talks to specific fields of research. The disciplines of mathematics and music share an intertwined history stretching back more than 2.5 millennia. More recently, computer science has made possible new approaches to these disciplines, often with transformative effect. In addition to the scientific program, there will be concerts, both Congress participants and to the general public. I will address about the last 3 decades in Mexico's history on this subject for those who do not know it or who know it come for the first time. Let me tell you that 24 years ago, I was listening at the radio station, a very nice voice that said something like the application of finite group theory to the musical analysis of Bach and so on so. So it called my attention, and when I went to see the owner of this voice, I went to the old building of the music school from UNAM, and this young thin man kindly showed me a bunch of papers he had. I read them and for some time, and I got the idea of what he was doing. This young man was Julio Estrada, a distinguished composer and musicologist. We will have the privilege of hearing him in a plenary lecture to close this conference. Then I went to Canada to do a PhD on algebraic K-theory. I was in love with pure mathematics like homological algebra, algebraic topology, algebraic geometry, homotopy theory. Nobody could have ever told me that these marvelous pieces of pure mathematics were ever to appear more than 30 years later in the other field of my passion, music. When I came back to Mexico in the early 80s, I wanted to do some work in mathematics and music, in particular to guide an undergraduate thesis to a student. But the large faces and terrible gesticulations of a colleague who was in charge of some high position at the department demoralized me from doing that. Sounds familiar? Some years later, in the 90s, a very decided lady, full of energy, appeared in my office, completely determined to make an undergraduate thesis in mathematics and music, particularly based on a book which I already mentioned from Julio Estrada. I gave her more articles and books, and she started to look for more bibliography. The librarian got some reference of Guerino Mazzola, particularly his book Gruppen and Kategorien in der Musik. Some articles by him and others, including Chemillier's papers, plus some of the American school. This lady was Mariana Montiel, here present, now a full professor in the United States. Mariana decided to do a master's thesis also in the same field, especially on denotator theory. I invited Guerino Mazzola to Mexico for the first time in 1997, and we began a wonderful friendship since. We know each other for 20 years, Guerino. That's a lot. My goodness, how fast time goes by. In the year 2000, when I was president of the Sociedad Matemática Mexicana, I dared to organize the first international seminar on mathematical music theory, which took place simultaneously here and at the Faculty of Science and in the School of Music of both from UNAM. Thomas Knoll and Guerino Mazzola attended, among others. Some days before the first international seminar, we have a previous special session on mathematical music theory at the annual Congreso Nacional de la Sociedad Matemática Mexicana in Saltillo, which had an assistance of about 2,000 persons, with great success. As a frame to both meetings, we had concerts by Guerino Mazzola in Saltillo, here in Sala Carlos Chávez, in Sala Xochipilli, here in Mexico City, which turned out into a delightful CD of free jazz called the UNAM Concert, with Guerino Mazzola playing Rachmaninoff's Corelli La Folia theme as a motive. In both meetings, many mathematicians and musicians attended with surprise in their face. The memoirs of the seminar were published by the Sociedad Matemática Mexicana, electronic publications, and lately were unified with the memoirs of the second international seminar, which took place in Germany in 2001, and with the third one, which took place in Switzerland in 2002, and published by Epos Music of the University of Osnabrück in the year 2004. I almost did not see the publication because I almost died. I was very ill for 6 months with an unknown disease, which later was believed to be a viral meningitis, for which there are no cure. So after not dying 6 years later, in 2009, a student of mine, young, impetuous, and talented mathematician and musician, Octavio Agustin Aquino, here present, convinced me to have the fourth seminar. It took place in Huatulco, Oaxaca in 2010 as the fourth international seminar on mathematical music theory. By the way, Octavio became the first PhD in mathematics graduated in Mexico at UNAM in mathematical music theory in the year 2011, with a thesis on microtonal counterpoint. In November 2012, another very talented man, musicologist, doing also systematic musicology, which I admire most because of his vast culture, talent, organizational capabilities, enormous memory, and many other talents, contacted me in order to organize a sequel of the international seminars, which turned out to be the very successful International Congress of Music and Mathematics held in November of 2014. This great man is Gabriel Parellón. At that Vallarta International Congress on Music and Mathematics, held in November of 2014, Guerino Mazzola proposed to me that the next MCM could be held in Mexico City at UNAM, and here we are. As you know, not only in Mexico, the funding for meetings is practically non-existent. Many persons interested in coming could not join us because they did not have economic support from their universities. We thought it could be obtained some funding for it, but once more, we had to do it with our own personal budget, forces and personal work and risk. We proudly can say that once more, we have done it by ourselves, thanks to you and to everybody that collaborated. I want to thank very especially Octavio Agustín Aquino and Mariana Montiel for their great work in the Scientific Program Committee, in which we spent hours and hours, days and more days working on it. Also, our thanks to all my graduate and undergraduate thesis students in the local committee for their assistance. We thank the collaboration for lending their infrastructure to the Faculty of Sciences here at UNAM, especially to the Secretaría de Difusión, to Alma Rosa Jiménez, and all her personnel. Our thanks to the technicians for their help in recording all lectures and putting them in our page the next day so anybody can see them. Also to Carlos Zamora for the transportation facilities and infrastructure. Thank you all for your kindness and attentions. Also, our thanks to the Escuela Superior de Música for lending their auditorium for Guerino Mazzola and Heinz Geiser recital tomorrow, and the Museo Nacional de Historia Castillo de Chapultepec for my recital with Harald Friepertinger on Wednesday. To finish these opening words, let me tell you that I work since the 70s with homotopy theory, cohomology theory, algebraic topology, homological algebra, among other fields of mathematics. In the 70s, this work considered pure mathematics. However, 37 years later, these wonderful pieces of mathematics come to be applied mathematics, and look where it happens to be in my other field of passion, music. But not only is an application, you can do new mathematics as well. For me, mathematics and music are both fine arts. They possess similar characteristics. To make this statement a lot more precise, Guerino Mazzola will give a whole inaugural lecture. In the name of the organizing committee and myself, we thank all the participants to the MCM for making it possible. Have a wonderful conference.
Dear colleagues, good morning and be very welcome to Mexico. I ask to address some words, and well, here. This is a very special occasion I would never have foreseen occurring during my lifetime when I was a teenager. The opportunity to gather in my country such an excellent group of researchers and enthusiasts in the intersection of mathematics, computation, and music, all of this as a member of the organizing committee. It has been a pleasure and an honor to participate in it. The significance of this conference is highlighted by the fact that two of my mentors, Emilio Lluís Puebla and Guerino Mazzola, reached special age milestones, and thus they can see and reap the fruits of the international and interdisciplinary scientific endeavor they have sowed decades ago. Perhaps I am not even a good example of the outcome of such a harvest, but nevertheless, I would like to offer my testimony as a tribute to these notable individuals. Early in my undergraduate studies in mathematics at Universidad Tecnológica de la Mixteca, I noticed that beautiful music seemed to be characterized by certain patterns and internal logic amenable to mathematical description and extension. I searched for less metaphorical work in that direction, and I stumbled upon with the trail of Emilio Lluís and Mariana Montiel. This in turn led me to the Topos of Music by Guerino Mazzola, and an ardent desire to study it, and writing my BS thesis
because in Mexico it's a requirement for graduation, on counterpoint. I profited from a field trip to meet Emilio Lluís here at UNAM and to propose him my plan of driving counterpoint to its ultimate consequences, for which I needed his support as tutor once I was admitted for graduate students at UNAM. I vividly remember him looking at me, trying to figure out my mental health. Luckily, his verdict was sane, and he gladly accepted to direct my MS thesis once I got accepted, and he helped me to get a copy of Mazzola's tract. And I remember carrying the 2-kilogram book around UTM, my alma mater, both as a motivation and as a source of befuddlement because of the deep mathematics it is based on. I wrote Guarino Mazzola for advice, and he simply answered, "Get your bachelor degree first." Thus, I did my best to excel at my courses and to convince a professor to direct my BS thesis with Mazzola's book as my personal bodyguard, but to no avail. Once I was a graduate student here at UNAM, I communicated again with Mazzola for some words of encouragement, and he replied, "Get your master's degree first." Emilio Lluís did not make this easy as well, since he instructed me to enroll early on in the algebraic geometry and topology, commutative algebra and category theory courses, so I can have a solid mathematical culture. This proved to be very hard for me, and many times I felt utterly lost with the material. But the topos of music appendices always were there to cheer me up. When I completed my master's degree and my hero, Guarino Mazzola, finally was my PhD director, I asked him again for a search direction, and he just told me, "You are on your own, boy." Lluís and Mazzola guidance, I realize now, was the best I could wish for. There is no royal path to mathematics and music. Hence, I should proceed steadily and carefully if I expected to succeed in my ambitions. I do not know how hard I can get, but I owe them a great deal of the epsilon I have managed to go forward. So I tell you again, to all of you, welcome to Mexico, and I hope we can have a great conference. And I ask you to big applause for these two men that enabled this. Thank you very much.
Well, we shall continue immediately after the microphone is given to Guarino Mazzola, so we can begin with the first plenary talk, which is called Mathematical Music Theory and the Musical Mathematical Game. So please, the technician, could you please bring the microphone? So we're going to prepare the things in just a minute. We are ahead of time, so 4 minutes, so we can do these things. ¿Está por ahí el técnico para que tenga el micrófono de solapa, por favor? I'll go down. They'll bring the microphone. If it doesn't work, do you use this one? I can also use it. No. Oh, but you wanted to move, no? No. You want to be seated? Ah, okay, then I'll give you this. Dice que se queda sentado.
Can you hear me here? Is that loud enough? Is it okay? Not too loud? Okay, so, yeah, let me start. Thank you so much for giving me the occasion to introduce here the whole topic. And the title is a little bit philosophical. It is Mathematical Music Theory versus Musical Math Game. So that's kind of a reversion of the roles. It's about the creative interplay of gestures and formulas in music mathematics. And it's a little bit philosophical, or should I rather say semiotical. The whole thing is, but also, of course, loaded by some technical aspects, which I'm not going to exaggerate here. So, first of all, I just want to give you some references to books on gestures and creativity theory. That's the 4 books I wrote until 2012, And you see the first book was La Vérité du beau dans la musique. This was the French book, and I think that was the first book where I introduced gesture theory. Then I wrote a book on free jazz and some on performance theory, and the one on music creativity in 2012, where I discussed the concept and the process of creativity in a more precise way. Now, the present state of the art, I think, is best represented in this upcoming 4-volume book. This is the second edition of the Topos of Music, and I think Springer will present it tomorrow. Ronan Nugent promised that they have a first reprint of this 4-volume book, which essentially adds the theory of gestures to the old Topos of Music. So that's kind of some references here. So my talk will have 4 parts. First, I want to talk a little bit about creativity and mathematics and music. Then I want to give some examples of mathematical creativity for music. Then I want to ask the question about the musical creativity for mathematics, and I think this is a topic which is very important, but it has always been kind of put aside because nobody knows how to deal with it. It's a difficult topic, so let's try to say something about that. And then at the end, I want to make the example of history and a little bit future of counterpoint. So, creativity in mathematics and music, and you can imagine that, musical mathematical creativity sounds like music, only there for inspiration and transpiration. So you see here the typical citation here, Einstein. He says that all great achievements of science must start from intuitive knowledge. I believe in intuition and inspiration. At times I feel certain I am right while not knowing the reason. I often think in music. I live my daydreams in music. And my approach is different from this one. I think I'm not talking about music as a kind of, superficial help, psychological help, kind of like drinking wine. You could also listen to music or play music in order to get more and more creative. My approach is more the question whether music can be more than just this inspirational device. And of course, I'm also opposed, in some sense, to Leibniz's very famous statement that musica est exercitium arithmeticae occultum nescientiae numerare animi. I think you know the English translation, yes? That music is only a superficial activity which is driven by the subconscious calculation of our soul. So I think this is kind of this one-sided perspective where music is just a consequence of a deeper mathematical reality. So I think I just want to relativize this very famous point of view. What is this strange sound here? Can you take that away? This dee. Please take that away because this is not the music I want to hear. Okay, so is anybody informed about that? Yes? Okay, I want to go on. I hope you can focus on what I'm saying here, because this is a good counterexample. The music is kind of not so good. So, yeah, let's start with the definition of creativity, which I've given in that creativity book. So that's a process which has 7 steps. So first of all, you want to exhibit an open question, and I focus on the concept of a question and not the problem. I think, oh, thank you. I think, okay, they are working on it. I think, yeah, let's be patient. So, yeah, that's the open question here, not the problem. So, question is more general, and I think for music, it's a good approach to just start with some kind of question. And then, after the question has been set up, that's really music now. You define its context. So, I think it's very important that you put your question or your problem into a context, and I think calling it a semiotic context is a good approach. So it's embedded in a science system, a system of meaningful things, and it's a question which relates to this context. You will see that the context is extremely important. Then when you are done with that, you find a core concept. So you look for kind of the core, the important central concept which, you know, gives rise to your question. And then you describe the concept's walls. So why am I talking about walls? Because a concept is, of course, delimited by its properties, by its attributes. It has certain, you know, defining properties, and that's what I call the walls. So the concept is kind of a box which determines what is outside of the concept, what is inside. So it's very important to find out what are the walls of that concept, yes? And I will give examples, then I first just describe the general procedure here. And then what you do is you look at those walls and you try to soften them. Finally. You soften those walls, you kind of try to open them, and they extend the whole concept. So you extend the semiotic context here, you add new meaning, yes? In that sense, it's a semiotic action. And to my mind, creativity is always essentially a semiotic extension. It's not just a formal extension. It's not flat, but you have to, you know, add some meaning. And then, of course, you evaluate this extension, and if you are happy, you solve the problem or you answer your question, yes? So I want to show, first of all, the typical musical situation where you act creatively. You start with, you know, rules in a given box, like, you know, I don't know, lead sheet in jazz, for example. Then you play that box live, and then you have a critique, yes? You feel that this is a limiting thing, and then you define new rules, you extend your context and your kind of technical devices, and you have new rules, and you play with this extended thing. And this makes clear that creativity has always to start from a given rule set. It is not just destroying things completely and starting from zero, but you have to know the old rules and then you extend them, right? So let me give two examples of a typical creative action. The first is Dr. Spencer Silver's 3M Post-it. Everybody knows the Post-it, yes? That has been invented in Minneapolis. And what was the problem? Silver was a chemist. He was trying to invent new adhesive, yes? So he was playing around with molecules, but he was not successful because the molecules were not giving really adhesives, what you think is an adhesive. It was kind of adhesive a little bit, but it was kind of not really working. And he had a friend who was a musician who had to take his scores and make notes on the scores. So he had to destroy the scores in the sense of gluing, you know, pieces of paper to the scores. And then he went to a seminar by Silver and he said, but this is exactly what I need. I need something which is not adhesive 100%, but a little bit less, yes? So what was the wall here? The wall was that for Silver, adhesive was kind of either 100% or 0%, yes? Either something is adhesive or not. And then his friend said, why should it be 100 or 0? It could be 50%. And this Post-it was exactly the solution, that you extend that conceptual wall, which you think is a definition of an adhesive. You know, and that's the critical thing, that the walls very often kind of show up like they were defining the concept. So it's kind of difficult sometimes to make this critical step to say, yeah, it looks like a definition, but it could be kind of a critical point. And the second example is Einstein's time, and this is exactly the same situation. You know, before Einstein, there was one time, yes, there was God's time, yes, everywhere one time. That was Newton's, God's divine time, yes? So if I ask you, do you have two weights? You would say, are you crazy? I have just one weight. And Einstein said, why should there be just one time, yes? And he said, every, you know, inertial reference system could have its own time. This is crazy, you know, but he just put into question this. And what was the wall? The wall was the singular mode of the concept of time. There was one time, you see, and it's difficult to find out why that should be a plural. So it's kind of difficult sometimes. The walls are really hidden because you think this is the very concept of what I'm talking about. So that's kind of a tricky thing. So Einstein said, no, let's have for every inertial system a time, and you transform the times using the Lorentz transformation, which is no longer kind of just shifting, but it's kind of it's kind of a linear transformation, which is not trivial. So he kind of solved that lot of problems by relativizing the time. Yes, I hope these are two examples which are significant. Yes. So let's go now to a more kind of specific example in our context, namely also an interesting wall, namely abstraction versus precision. You always think when you go abstraction, you have to be precise, of course, yes? So let's look at the construction of the integers from fuzzy gestures, yes? Now, you know that you can look at homotopy classes of loops in the circle. So you have the circle S1 here, and you look at those loops which start at 1 and end at 1, yes? And they can go n times. And the construction here is that you think that the integers are just, going around n times from 1 to 1. And you think, okay, but that's perfect. So I go around n times, and how do I add? I just concatenate going around, yes? So I take two loops and then concatenate the second to the first. So that's the addition, but that doesn't work. It doesn't work because in this way you don't get the associative law of integers, yes? So the arithmetic of integers doesn't work if you take this kind of precise concept of loops, right? What you have to do is to make these loops unprecise in the sense of, well, it doesn't matter how fast I go around. I can also go backward a little bit, forward a little bit. So I can kind of move around in a certain elastic way. And when you do that, yes, and then that's what is called homotopy classes, then you get the associative law. So the precise abstract integers, yes, are defined not by precise, mathematical loops, but by kind of fuzzy, elastic kind of derivatives of such loops. So I think this is an interesting wall that you can create abstract stuff by losing the precision which you thought is. I think this is an interesting example, yes? So you had this kind of gesture going around, and it can be more or less fuzzy. And of course, the very interesting general setup is this theorem, yes, that every group, so every abstract group, right, no restriction, every abstract mathematical group is isomorphic to the fundamental group, pi1, of a topological space. So the fundamental group means you fix a point, yes, and you take all the loops which start at that point, end at the point, and you concatenate those loops. And you look at homotopy classes of such loops. And if you find a nice space, and we will discuss that later here, then you can construct a group which is isomorphic to a given group. And I think this is a fantastic kind of fuzzy representation of the abstract group theory. Yes, so this is it, and it of course has musical applications. Let me just give it now. Let's again take this gesture of the loop going around from 1 to 1, and the pi1, so the fundamental group of the circle is z, the integers, yes, and that refers to what I call gestoid in my theory, but I'm not focusing on that, it's just a reference. And now you look at the group algebra, yes, which is just, the vector space, which is generated by this group as a basis and the complex numbers as coefficients, yes? And you look at that one, and this is a completely musical thing, yes? You take the fundamental group, you take now these rotations, and you interpret them as an exponential function, yes? And then you have this kind of formal sums. This is an element of the group algebra, right? But this is something everybody knows, yes? This is the Fourier. So you see, you come from this kind of abstract nonsense of a group, yes? You immediately come to music, and you will see later here that this can be generalized for any group. So I think this is an interesting thing, that group theory essentially can be representing music. I think this is an open question. This is not solved, but I think I have some ideas about that one. Okay, so this is creativity in math and music, just a general introduction. Now, example of mathematical creativity for music. Okay, Now, I was working with the Kinderszene number 1 from of Schumann's Kinderscenes von fremden Ländern und Menschen. And here you have Argerich playing this wonderful piece, yes? And so on. So what I did is kind of create a new piece, which I called Mystery Child, and that sounds like this, yes? So this is not, to my mind, not an example of creativity. And here the context is very important. I used the MIDI file, you know, of the Schumann piece, and I put it into the software Rubato, not Rubato, Presto, which deformed this MIDI inputs, this set of MIDI objects in a geometric way, deformed them, and then changed the instruments, yes? So if I have that software, this is not creative for me anymore. Of course, this could be creative for somebody who has absolutely no tools of that type, yes? But if you have the context, which is this kind of software, I think it is no longer creative. So I think it's very important to see the context, yes? If you have a chimpanzee who has to pick up a banana somewhere, you know, it could be very tricky to find the banana, the way to grasp the banana, but for us it would be trivial. So I think the context is extremely important here. So that's an example. And another example was my composition Synthesis, where I also used this software, and I was playing the piano, but essentially it was, to my mind, not really creative. Except my piano, perhaps, yes. So all the drum and bass things were constructed by mathematical tools, and I would not consider that as being creative. You know, I think I mean, you understand what I want to say here. The context is extremely important, yes. You know. Okay, so now I want to switch over to an example where I think, for my context, it was creative. I was analyzing Hammerklavier Sonata by Beethoven, yes? This very famous, you know, the Mount Everest of sonata creativity in classical music. And I made now a mathematical analysis. So in my theory, I described the modulation structure of Opus 106 as governed by the symmetry group of the diminished seventh chord, which is represented here in the role of admitted modulation forces. So I used a mathematical model of modulation, and then I got, you know, using these symmetries, I got two orbits of tonalities. One has 8 tonalities, and the anti-world has 4 tonalities, and then I could describe all these different modulations in the development and etc. in all these parts here, using this whole theory. So that was kind of a mathematical analysis of the first movement of the Hammerklavier, using mathematical kind of group theory, small group theory stuff, yes? And then so I transferred the musical ontology to the mathematical ontology, and I think that's a really very different way of thinking, yes? Using that, I had now a very easy, you know, kind of procedure in the mathematical sense, because the Opus 106 was using the symmetry group associated with the diminished sevenths, yes, the minor third, which is associated with the Messiaen 2 scale, And so for a mathematician, it's evident how you would change this to create a new composition, yes? Because you know that the Z12, of course, is the direct product of the two Silov subgroups, Z3 and C4. And here I have C4 here, so why not take C3? So I just took, you know, in my opus 3, which I composed, I took just the symmetries of the augmented third and the corresponding Messiaen 3 scale. So, I mean, mathematically speaking, that was kind of an easy way to think of creativity on the mathematical procedural level, yes? So when I got that, I described the modulation structure of opus 3 by the symmetries of the augmented triad, this one, which is represented here, for the modulation forces. And here you have 3 orbits, you know, of tonalities, which are given by the symmetry group. Here are the orbits. And then you can construct the exposition and things like that, and modulations, and the details are not important here, but important is kind of this transfer of a kind of a structure, yes, on the mathematical level, yes. So I was not really musically creative here, I was just working on a mathematical level, and I constructed some first movement of a sonata here. This is described in my first book, published in 1985. Of course, I was kind of very proud of, you know, using the orbits, the automorphism of Messiaen 3 divided by, and all that stuff. In 58 pages, you can still read that, and there is no other place. Unfortunately, I didn't publish anything after that. That's written in German. Okay. So in 2003, that was also recorded and published. Patrizio Mazzola has recorded this movement. And here you see the two movements. Here is the sonata, first page. This is Pollini, of course. This is my preferred performance. So on. And my composition, which I called L'essence du bleu, starts like this, a very similar start. So on. So this is this kind of thing I did. And now I think this is, for me, a very typical procedure in mathematical music theory, yes? So I start with the musical object opus 106, right? Then I make a mathematical transfer, so I go to another ontology, which is the mathematical ontology. I see that group, I change the group to a new group, and I go back and create a new musical object. So you have this kind of transfer into the other ontology and coming back, yes? So this is typical mathematical music theory, and you see there are two ontologies, the musical one and the mathematical one. Now the wall here, what is the wall? The wall is, of course, Beethoven, you know, in the sense of, would you try to compose a sonata which is kind of higher than the Mount Everest of sonata theory? And of course, that's the top. You cannot be more creative on that. So that's kind of a wall. It's finished. You cannot do that, yes? You know, that's kind of the common understanding of the Hammerklavier. So what I did, yes, was go into another ontology of mathematics, and there it's much more flexible. You can, you know, it's one group, you have another group, you know, kind of no problem. So you can work there without kind of being afraid of Beethoven and all that ideology. So I think that's an interesting thing. You see that the ontology change is very important here. Yes, you go away from the musical realm, yes, and you go somewhere where you kind of work how you like to work, yes. And then you go back, of course, everybody said, you know, why do you want to compose another sonata nowadays? Nowadays, you don't do that anymore, you know, it's not fashionable. And I said, it's a very stupid remark. You know, if you would discover Opus 112 by Beethoven, piano, everybody would love it. I mean, it's an ideology. Okay, I'm not saying my sonata is an interesting one. It was just an interesting experiment. But I think it was kind of a success in the sense of that this change of ontology, yes, was possible and could also produce some kind of real music, yes. Now, the second example here, I think it's more related to the counterpoint topic today, namely the Pythagorean tetractys. Yes, if you look at Pythagoras, you know, he was working with monochord. They were listening to those intervals you can generate when you pick and you know, and you look at the changing the length of the chord, then you can get, you know, higher and so on, you know, the whole thing. So they were working with this monochord. Yes, this is the music one. Now what he did a very ingenious thing. He invented the world formula of ancient Greek, philosophy and physics, I would say, you know. He said that the very basis of our world is some kind of abstract entity, which he called tetractys, which is composed of 10 points. 10 is the holy number in ancient Greek philosophy. And it is a layering of 1, 2, 3, 4 points, yes. And you see numbers appear there, 2 to 1, 3 to 2, and 4 to 3. And everybody knows here that this is related to the octave, yes, the fifth, the just fifths, and the fourth. So you get a mathematical description of those kind of intervals they were hearing on the monochord, yes. So you get that one, and so you get kind of a mathematical interpretation of a musical reality. And then, of course, you have the development of all those mathematical things which come when you start talking about fractions, yes? You have the whole idea of mathematical structures which are fractions, yes? You get all these interval ratios, and I would say, you know, with the time in the middle of the Middle Ages, you had the whole, you know, zoo of intervals which were described by these fractions. So you had a whole theory of intervals which was kind of controlled by this mathematical language, yes? So you have this kind of typical mathematical music theory thing. You start with the music, you go to mathematics, and there you work out something and you come back to some musical category, yes? And I think you have in the musical ontology here and in the mathematical ontology two very different situations, yes? What is the wall here? I mean, to be honest, you know, when you play the monochord and you are Pythagoras, yes, you don't know anything about acoustics. You don't know anything about Fourier. That is absolutely nothing. I mean, it's not that they could, oh yes, let's talk about overtones. They didn't have anything. So I think that was a very interesting wall, yes? They were just stuck with this kind of phenomenon. And he moved into another reality, and playing around with those fractions generated this kind of category of, not in a mathematical sense, but just this set of musically interesting intervals, yes? Okay, this is the second example. Now, the third example is also related to counterpoint. You remember that, you know, with Fuchs and Palestrina, you had this kind of result of all this research, I come back to that, which, you know, divides the intervals into 6-element sets, the consonances, you know, the prime, the thirds, the fifths, and the sixths, and then the other 6 intervals are dissonance. And this was kind of a result. And now, how can you deal with that? How can you create creative action? Now, what you can do is, of course, try to understand this dichotomy and make a mathematical model, and this is what kind of started my interest into counterpoint, yes, that you go to the torus of thirds, you look at the symmetry between the consonances and dissonances. This is this 5k plus 2 on the third torus. You have very nice geometric property, and then you do mathematics, yes? Then you are in a small group theory, a little bit of kind of topology, and then you say, okay, but in mathematics, you know, which deals with generalizations, you can say, oh, but there are other dichotomies which have similar properties in the sense of, you know, a symmetry and some geometric properties, and you end up with 6 possible, what I call strong dichotomies. So you invent a mathematical entity which is kind of 6 counterpoint worlds, yes? And then you go back and you write books and you implement software, and this is implemented here in our Rubato software by Julien Junot. And of course, Octavio has written very interesting things, generalizing the whole thing to microtonal counterpoint, yes, which is a very kind of a new thing, because if I tell you, okay, how would you generalize normal counterpoint to microtonal situations, yes, to quarter tones, to fifth tones? There is absolutely no idea from the musical point of view, yes? And this is kind of the point that this is on the musical ontology, yes, the Palestrina-Fuchs dichotomy is a dead end. It's a dead end in any sense of the word, yes, of the word. The musical ontology finishes there. If you go to the schools of music, what you have a counterpoint course there, yes, and they tell you, the fourth is dissonant. In the first species, they tell you the parallel of fifths are forbidden. And I ask all my students, have you ever asked your professor why this is the case? No, we just, we have to make our credits, of course. So the point is, nobody really questions, and in mathematics or in physics, that would not be possible, yes? You would ask, why is this damn it thing dissonant or consonant? But in music, this is kind of an ideological dead end, yes? You have this counter, and there is no progress. It's fixed since Fuchs, Gradus ab Parnassum. I think this is would never have happened in physics and mathematics. People don't care, but I think this is a catastrophe. This is a catastrophe of educated humans that they never ask why this damn it fourth is dissonant and why the parallel of fifths is more boring than the parallel of thirds. It's kind of psychological. So it's a whole mess here. So what we did, we just went away from the musical thing and said, okay, what is this mathematically speaking? And in that world, we could just add new kind of understanding of this thing, of course. Of course, there is a lot of objection against this. This is a good sign, When people are against it, it's always a very good sign. So that was this other example. I come back to the counterpoint later. So now I think I want to talk about musical creativity for mathematics, yes? So this other direction. Now the question is, can we expect creativity in the opposed direction? So you remember Novalis, Fürst von Hardenberg, was a very important romantic philosopher and writer, and he was talking about musical mathematics. And that's the reason why I would call the other direction the MUMAG GM, the musical math game. Attention, it's not a theory, it's a game. I think that's a very important difference. I'll come back to that. Now, Franziska Bomsky has written an interesting dissertation where she says that Novalis, I should translate that to English, sorry. Novalis is not interested in inventing new contents or truths, but to understand or invent the rules for the art of invention as such. So I think this is a very interesting approach, that he wants to find out, how can we invent new things? Is there kind of a methodology? So I think Novalis is a very interesting reference here. So the idea would be now, what is the idea? Start with a mathematical fact, yes? Transfer it to a musical fact. That's the reason why the music comes back now. Make some kind of transformation on the musical level, and then go back to the mathematical level, and then you get kind of this movement, which is musical math game. So you play music, of course, yes? You don't make music theory, you play music. So that's the question. So is this possible? I come back to this relating to counterpoint, but I first want to talk about the relationship between music and mathematics, and I know some of you know it, or know some of it, but I think I have to recall some of it. So some ideas about relation in mathematics and music. So this is my ideology, to be honest. I think we have two poles of cognitive activities, formulas and gestures. And to my mind, mathematics and music deal with both, but in a different way, yes. So the idea is that you have here the world of gestures and you have the world of formulas. And the leading idea would be that mathematics takes gestures, so you calculate, you make gestures as a mathematician, and the result is a formula, yes? Like the Weyl conjectures, these are all formulas, yes? or all this Euler formula. So that's kind of, you create as a result, yes, you create formula. While in music, you go the other way around. You take formulas like, you know, a cadence formula or a modulation formula, which tells you some abstract symbols, and then you create a composition, yes, which unfolds that formula to real music. So the mathematicians take gestures, they compactify them, they build formulas and rules. And in music, you unfold formulas, you apply formulas, and you create a gesture. Yes, this is my kind of background and ideology. Now, just to specify what is a gesture here, because gestures is something which is not very classical. For me, a gesture is a digraph morphism from a digraph gamma to a digraph of continuous curves. So you have a topological category, you have all the continuous curves in that category, and these are the arrows. And then you have, the starting and the end point, which are the 2 points of an arrow. So the digraph X with that arrow is the set of all those continuous curves. And you have a morphism from an abstract digraph gamma into that digraph of continuous curves. And I think it's easier to understand when you see the image. Yes, take just this directed graph you see with four vertices and then this set of arrows here. And then you map this abstract thing into a set of curves. So all the curves, the red ones, are images of the abstract arrows. You see, for example, can I show it here? Oh, God. Here. No, I don't want to show you that one. Okay, sorry. Here you have this loop here, you see, and the loop here is mapped into this continuous curve here. So you see this is kind of a continuous image of an abstract thing, and I call the left thing the skeleton of the gesture and the right thing the body. Okay, and one more slide concerning gestures. You can also look at gestures of gestures, which are called hypergestures. This is a simple topological fact, because the set of gestures is again a topological category, so you can look at gestures of gestures. And my classical example is in space-time, you take in the space just this loop, and then you take a tripod of such loops. Can you imagine what is a tripod of loops? Yes? So you have a tripod, and all the points are just